Hello everyone. We are talking about digital modulation techniques, and this is a binary modulation technique. Here we are talking about the simple circuit which is going to produce uh, binary digital data in terms of carrier signal based on its amplitude, frequency, and phase. So as it is amplitude shift keying, frequency shift keying, and the phase shift keying. And for that, we are using a simple CMOS switch. As we are seeing it, it is 4051 is a CMOS switch, which has been used over here as MUX. I can use it as DMUX, but it creates a channel to select your carrier with the help of select line, and then it produces your output as it is required, either amplitude shift keying or frequency shift keying or phase shift keying. So one single IC which is very simple, low profile, low cost, low power, but it is going to be used for lots of applications. So let's see, this is amplitude shift keying. The two magnitudes we have decided they are supposed to be produced over the transmission line based on our logic data. This logic data could be, it could be unipolar, it could be bipolar. Normally we say for ASK unipolar is sufficient, but here the option is open for us. So when the pin number 13 is a directly the magnitude is there, and pin number 14 is the low magnitude signal is there. So when the logic 0 comes in, the low magnitude is being selected and high magnitude is being selected on logic 1. So the waveforms they are showing it. Here in this output waveform, we are showing it as logic 0 is a 0 magnitude, but this we can vary it because we are using the potentiometer. So next, if we'll just see to it, it's a frequency shift keying. What we are trying to do is corresponding to logic 1, the one particular carrier should be there, and for logic 0, there should be another carrier. If these frequencies are being selected on the two carrier as carrier 1 and carrier 2 onto the two inputs of our CMOS switch, my select line where the logic data is being given to the pin number 11, that will select, and you are seeing the two carriers. If the carrier is being varied, then the output will remain same, only internal carrier will vary. This frequency shift keying will change based on the digital data. Next, similarly, what we have tried to give it for phase shifting. When the logic data changes, then the phase of the carrier should be changed. No magnitude, no frequency should be varied. And exactly that we have followed. In one channel, we have given the one carrier, and on the other channel, we have given the 180-degree phase shifted. Unity gain op-amp we have used in inverting mode. It's a very simple, and then my logic data has been given to pin number 11, and which is giving me the phase change. Whenever there is a logic change is there you will find the output, there is a phase change. Whenever there is a logic change is there is a change in the phase. So this is the simplest of the circuit which we can find and generate the three different binary phase shifting. And this mux can be used for QPSK, can be used for MRA PSK, can be used for MRA ASK, can be used for MRA FSK, all sorts of application. So this is just uh, a general discussion to help everyone, whoever is interested can develop multiple applications. Thank you.
2 kilohertz with the peak to peak of 120 1.2 volts without offset, and second channel is again given 1.2 volts with 5 kilohertz, and the low frequency data pulses are given, which is of 500 hertz, and if we'll just see to it, corresponding to logic 1 and 0, there is a high frequency and low frequency, and this magnitude keeps constant, so it's a frequency shift key. And if I change the frequency of one channel, only one corresponding to logic high, this frequency is being changed. Corresponding to logic low, there is no change in the frequency. And same as we can just check it with logic low. During the logic low, just see it's, so it's a frequency shift key corresponding to logic 1 and 0. And if suppose the frequency of logic data, if we wish to change, see when the logic 1 and 0, if their timings are getting changed, high and low frequencies timings are also getting changed. This is frequency shift gain, and here if we'll see the circuit, this CMOS switch has been used. For one carrier, one switch has been used, the another carrier, another switch has been given, and the selection is done through the select line as normally we do it for mux demux. So it's behaving as a phase shift key.
Repeat it.
This is FSK on time domain. Corresponding to logic 0, there is low frequency of 2 kilohertz, and corresponding to logic 1, there is 9 kilohertz carrier frequency. This is in time domain. Let's see this spectrum. हाँ बैठे बैठे let's select the two cursor on our spectrum. This is the second cursor, and let's select the first cursor. First cursor is corresponding to 2 kilohertz. Second cursor is corresponding to 9 kilohertz. And if I just see, let's say take the example of cursor 1. This is the first, second, third, fourth, fifth. These are all side bands, and if I just see to it carefully, first upper side band 2 kilohertz, 2.5 kilohertz, and lower side band of first fundamental frequency, it is 500 hertz away from the center frequency. Then the second harmonics is at 1 kilohertz. Rather than 2.5, it is 3.5. Then 4.5. Then it is 5.5. Then it is 6.5. Then 7.5. So like that, the entire spectrum is available. The magnitude of the center frequency and the magnitudes of sideband, not much of a difference. So it means these all sidebands are significant. So the bandwidth of FSK is a huge, very large band. Similarly, I can check it for cursor 2. This is at 9 and upper sideband at 9.5. Then at 1 kilohertz away, 10.5, 11.5, and so on. It is going to be increased. So the entire spectrum is very, very huge. Huge bandwidth is there. So this is the spectrum of FSK.